Hello everyone. In this video, let us try to look into the pulse width quality check parameter of the clock tree network. So in this clock tree, if you see the wire drawn from the clock port to the flip-flop clock endpoint, those are actually real wires. Those are actually physical wires which are placed on the chips. They are basically metal layers, something like this. So they have got some physical dimension, they have got a length, and they have got width, they have got some finite width. So due to this, they become a very good component for resistance and capacitance. What I mean to say is, all this particular the complete area from the clock port to the clock endpoints, it's filled with some values of resistance and capacitance, because these wires have got some finite resistance and capacitance. So anything which has got a physical dimension, in our case it's the wires. So wires, since they have a physical dimension, they have got a resistance and capacitance that is associated with this particular wires. So for example, resistance is nothing but R is equal to rho L by A, and capacitance is nothing but C is equal to epsilon A by D. So if you see anything which has got a area or a dimension or a depth or a height, everything, anything like that has got a resistance and capacitance which is attached to them. And in this case, the wire resistance and capacitance will look something like this. It will be the complete net or the complete wire will be full of a bunch of series resistance of capacitance. So all the RC network will be connected in series in the complete net. So this is how the wire looks, and the clock signal which is present over here, it has to traverse through this complete RC network and reach over here. So for this, let us try to briefly understand a small RC network. So for example, if you take a resistance and a capacitance, if you take a capacitance and resistance and connect both in series, and if you apply a step input at the input of this particular network, at the output what you get is a charging waveform for this particular capacitor. So basically what I'm doing is I'm just providing a step input, and at the output you get a waveform which is charging, which is nothing but the charging waveform across the capacitor. So it means that this capacitor I'm continuously filling it with charges. And when I fill the capacitor with charges, the voltage across the capacitor increases, and it increases in this form. It's not a straight waveform, but it's a ramp. It's kind of ramp waveform. So this is the basic functionality of an RC network. Now you can just imagine, if you apply this particular waveform again back at the input of the RC network, how the waveform at the output will be. So for example, there is one more RC network which is connected over here, and if you apply this particular waveform at the input of that RC network, the output capacitor will be charging, but the charging will be even slower. So basically this is what we are going to look in the next slide. For example, you apply a waveform something like this of a sharp transition or a sharp slew. If you apply this particular waveform at the input of this first RC network, the output of the RC network will be a ramp, but it will be not a very good ramp, but it will be a ramp which has got an output slew or output transition which is slightly worse than this one. Okay, when you take that waveform and apply at the input of the next RC network, the waveform will be even bad. And eventually, when this particular waveform reaches traverses through this particular complete RC network, the waveform that you see at this point will be like this. So it has a slew, but the slew is very worse. It's like so for example, if this was like let's say if this was like 50 picoseconds over here, this will be close to 150 or 200 picoseconds, or even worse than that, because over here we are looking into a small chip, we are looking into a small area, that is, it has to move from only this endpoint to this endpoint. But on a chip where we have like millions of flops, so it has to traverse through the complete chip and then reach over here. So what we have drawn over here, it will be even worse in a real scenario. It will be even worse. So in this case, if we are trying to check for a pulse width check, if we're going to check for a pulse width, we have to send the next signal also. We have to send the signal which is like rising to falling edge. If we send that particular signal, the waveform that we get at the output is something like this. It's again, the reason is again the same, because it has to traverse through the complete RC network, and hence this is basically the RC time constant. The discharging time is basically the time constant that it requires to discharge the capacitor. So this is the waveform that you tend to expect at the output of this particular clock tree network. And this is true not only for this endpoint, but for all the other endpoints also. If you look at any of the endpoints and you check and you probe for this particular, and you probe any other endpoint for waveform, you will see that this is the waveform that you will get at this particular endpoint, or at this particular endpoint, and so on. Now, when we are trying to check for pulse width check, the thing that we did was we used to send a pulse of width, let's say 500 picoseconds over here, and the clock tree was expected to provide a pulse at the output exactly as 500 picoseconds. It could be more or less, but but within some range, not in this range. So over here clearly the input waveform is 500 picoseconds, but the output is not 500 picoseconds. The output waveform is much more than 500 picoseconds if you actually see over here. And this is not only true for this endpoint, but for all the endpoints. So for a pulse width check, when we are checking for a pulse width, this is the width that we are checking for, and clearly we see the output pulse width is a clear no for us, because the reason why we are doing the pulse width check is for applications that work on rising as well as falling edge. But in this case, if we have a waveform something like this and provided at the clock endpoint, this is a big no for us, because we are actually doubling or tripling the frequency. How we are doing that? So for example, at the input you have 500 picoseconds, the other waveform will be also of let's say 500 picoseconds. So this complete waveform becomes of 1 nanosecond, which means it's like 1 gigahertz. Now this particular thing, if you see, it is let's say it's double, it's not 500 picoseconds, but it's more than 500 picoseconds. Let us take a number, it is 1 nanosecond. The pulse width over here is 1 nanosecond. The other pulse width which will be coming over here will be again 1 nanosecond. So you have 1 nanoseconds plus 1 nanoseconds, which is like 2 nanoseconds, and the inverse of that is roughly 500 megahertz. So you can do a calculation, 1 upon 2 nanoseconds, it comes to roughly 500 megahertz. So if you see, there is a drop in the frequency. The frequency that was expected from the input was 1 gigahertz, and the frequency that it get at the output is 500 megahertz, and it's a huge drop, and it's a huge loss for a high speed circuit, which is not acceptable. So we have to do something about it. But for as a checklist point of view, this particular checklist it's a clear no, it's a red cross for us. The pulse width check we are not meeting. But if on the contrary, if you try to quantify this particular waveform for the duty cycle check, what happens is you will see the waveform which we are going to send the next, which is this one. This has got at the input, it has got 50% duty cycle. We are agreeing with that. And again at the output, when you send the same kind of waveform again at the input, the waveform that you get at the output, or that you expect at the output, is also like this. And fortunately or unfortunately, the duty cycle that you get at the output waveform is 50%. But as we said, this 50% duty cycle doesn't make sense for us, because we are not meeting the pulse width check. So and remember me saying that the duty cycle check was the comprehensive check of the pulse width. So when we do a pulse width check, and if we are going across with the pulse width check, then we go for a duty cycle check, which is again a more comprehensive check of the pulse width itself, to make sure that we are actually getting the 50% duty cycle or 52% duty cycle, that kind of thing, to quantify the loss in the duty cycle. But in this case, we are getting the actual duty cycle, but it doesn't make any sense for us. It's as simple as that. So for us, the duty cycle check, if you actually see the duty cycle check, we can say it's a red tick. Why a red tick? It does meet, but it doesn't make any sense, because the point number 2, which is the pulse width check, we are not meeting with that. So it's as simple as that. So next, we are done with 3 checks. So what we'll do is, since I'm running out of time, we'll talk about the latency and the clock tree power. We'll be looking into what will be the value of latency and what will be the value of clock tree power. Or in general, we'll discuss about the latency and the clock tree power value and the signal integrity and crosstalk check. So signal integrity and crosstalk check will be, it's a huge topic. It's a separate topic by itself. This particular thing, it's a separate topic by itself. So we have a separate class on signal integrity and crosstalk, where we'll be looking into all kinds of issues for this one in that particular videos. So in this sections we'll be looking into mostly the five quality checks, that is Q, pulse width, duty cycle, latency, and the clock tree power. And 6th one we'll be looking into detail in a separate class of videos. So for now, let us stop over here, and in the next video, let us try to look into the latency and the clock tree power topics. Thank you.